So by all means. So I also might have a few more slides than what I normally put. Again, I'm trying to be honest to my student who put a lot of effort in preparing them. So if I go a little bit over, I'll skip some of the steps and you can always ask later. So we're going to talk about the community detection problem in a stochastic block model. And I say it up front from the beginning, I'm going to talk about a very, very simple scenario. Everything goes through in way more generality, but we wanted something nice, something pretty, and for some reason, something very elegant with nice Q's and P's and little constants that you can see explicitly. So if at any point it strikes you as it feels a bit artificial, then yes, I agree, because I know that there's a lot of practitioners here that might take that point of view. So just bear with me. It does go through more. There's a lot more, but you know, it looks pretty when you have nice, clean constants. So I'll keep it that way. We're going to take a random graph, G, with sort of vertices E, sort of edges E. The cardinality, I try to be consistent. Sometimes I use N, sometimes I use the cardinality of the set, but you should be able to follow along. And each vertex in this graph is going to have a community label. And for the purpose of this talk, we're going to talk about two communities only, so labels 1 and 2. The labels are given a priori. They exist on some other type space, or as you want to call it, an attribute space, and are usually going to be unknown. I'm going to call the label, oh, I did it. See, it didn't take me any. Wow, okay, so that was a Control L. Wow, I was fast in falling into a trap, huh? Anyways, so we're going to have two communities, and JI denotes the community belonging or the community label of vertex I. And this is a sparse graph. So my connection probabilities on this model are going to be of the form a constant over n, so that the average degree is always just a constant. And then we're going to have two parameters. This is a symmetric connection case, even though we're going to be talking about directed graphs, where the probability of having edge I to j is going to be of the form A over n if the two vertices belong to the same community, and it's going to be B over n if they belong to different communities. And the idea is we're going to try to make sure that A is bigger than B, so that we have this notion that people from the same community are more likely to be connected with each other than with members of other communities. Edges are drawn independently of other edges and independently of anything else, of the attributes and the labels.
Edges can actually exist both sides.
Yes, edges can exist both sides. We're going to be talking about the directed. There's a little D up there, yeah. And you know, this is an interesting question. Most of everything I've ever done and that my students have done with me is on directed graphs, and there's a very good reason for that. But it goes a little bit more into these local weak convergence and passing certain limits through, and I would love to talk more about it later, but probably not in the context of this talk. But yes, this is all going to be directed. And as I said, we're going to focus on the assortative case, where we assume that people from the same community are more likely to be connected to each other than to people from the opposite community. And again, everything generalizes, just not quite going to do it right now. We have the standard in the study of stochastic block models, or directed stochastic block models for that matter, which is the kernel matrix, or kernel in the general case. In the more general case, it's just a kernel in a potentially very complicated space, metric space, polished space, whatever it has to be. But in this case, it's very simple. It only has two communities. And as I said, we're going to make it symmetric. So this is my kappa, probability of connecting A in the same community and B across opposite communities. We assume that the labels are unknown to us. They exist in the God world. Somebody knows up there what it is, but we don't know what the community labels are. Our goal, as it often is the case in this kind of problems, is to try to guess the community labels from what we see, from the edges that are observed on the graph. And in this particular variation of the problem, we're going to assume that we know a few members, or a positive fraction of the members in the community. And if you think that this sounds a little bit crazy, well, I was told yesterday not to talk about politics, but in America, everything is politics, and a lot of people like to advertise it, big signs across on their lawns. Everybody knows, everybody wears their label. Not everybody, but like a very large fraction of people do. So if you think about it, we're talking about politics, and I did it again. When we talk about politics, it's not uncommon to think that we do know a fair number of people's labels, and I'm going to assume that that is the case here, right? And what I'm going to talk about is one particular algorithm for community recovery that is going to be very fast. It's local. It scales beautifully because it's not a spectral method. No eigenvalues, nothing is being computed. It can scale beautifully to any size, millions of nodes. Why? Because you can run it in a distributed fashion. Doesn't even have to be. So in that sense, I'm not trying to say that it's the best or that we're going to do anything close to perfect recovery, but it scales, it's fast, and it's pretty. Yes?
Yeah, so I just wanted to make sure that I understand the setting correctly. So now I understand that you know the seeds, and you know that the matrix kappa is symmetric. What else do you assume that you know?
I don't actually need to know kappa. All I need to, in this particular, for these examples, I will assume that the communities are balanced. That's again just to make that things look pretty. None of that is really necessary. My other co-author is more of a pure mathematician than I am, tends to love things that are pretty. Our students sort of tends to like things that look pretty. And, we ended up with something that looks pretty. But, none of it is really, truly necessary. And I can explain a little bit later.
Yeah, so you don't need to know balance of communities, and you don't need to know anything about kappa except that it exists.
Right. Okay. And for the results, you'll see that I am using, I'm assuming that I know the values of A and B and that it's balanced.
Oh,
in the results, but again, I'll make some comments about that because I don't want to put too much applied focus on what those results are supposed to tell you. So I'll get to that, and I promise to address that question. So let me just give a quick overview of what is known in this setting. In this setting, there's basically two sets of very classical results at this point that tell us when recovery is possible and when it's not. In the semi-sparse regime, where edges are growing at the order a constant log of n over n, standard sort of what we call usually semi-sparse, recovery is possible under the assumption that the square root of a minus square root of b is greater than 2, and it's known to be impossible otherwise. So that's the first of those known results. In the sparse regime, where the expected degree is bounded, and this the same case that we are studying, the same question was addressed in two different parts. For the positive part, this is work of Masuli in 2014 that says recovery is possible when in the sparse setting, when this other condition, a minus b squared is greater than 2 times a plus b. And the converse is also known, and also came soon after, Mosel, Niemann, and Sly, that says that under that threshold, it's impossible. Right? So these are just the context of what is known. These are undirected. Just to be sure, by recovery here, you mean that better than random guess? But I think the second and third are better than random guess. The one on the top is exact recovery. Yes. And the second one is for giant component. Yeah, I think so. Yeah, I'm gonna have to double check on that. Again, these are not my slides, but yes, I don't think it's exact recovery for that one. Yeah, it's weak recovery. Okay. Other people know better. Yeah. So the one thing that I do want to call attention to is that when the recovery is possible in these settings, it usually implies this heavily intensive spectral methods, right? Eigenvalues, eigenvectors, things that are often hard to do. It's also diffusion method like PageRank. Is that what it is? I thought it was a spectral. It's like a study of this backward, the non-backtracking graph and the spectral properties of that, isn't it? Anyway, we can talk about it later. I'm not going to go. Okay. So I guess just to say that why would one want to consider other things? Again, I'll go back this method doesn't actually require computing anything that is hard to compute. That's the main idea. So in that sense, it scales very, very nicely because at the end it's PageRank. And PageRank is very efficient and it can be run in a distributed fashion asynchronously, and it still converges to what it has to converge. So in that sense, that's the value of the method. So let me talk about what the specific PageRank Nibble algorithm is supposed to be. So we have the graph. It's going to be assumed to be directed. We have a fixed damping factor C. It's going to be strictly between 0 and 1. This is going to be one of our parameters, so I'm going to leave it as an open thing to play with later. And we're going to run PageRank, standard PageRank or personalized PageRank on our graph in a special way. So let me just quickly go over what the PageRank recursion tells us. It gives us the scores, the PageRanks of the vertices in the graph that are obtained by solving a system of linear equations. This system of linear equation, what it's doing is taking weighted averages of the ranks of the inbound neighbors, and it's using a personalization value Q. So the Qs are often assumed to be a probability vector. For the purpose of what we're doing, they don't have to be, and I'm actually gonna not use the fact that there has to be a probability vector. But in one of the interpretations, it is supposed to be to give it the random walk sort of flavor to it. This Q is called the personalization vector, and that's what we're going to use to create the PageRank Nibble algorithm. And in the standard PageRank, of course, we have that the personalization vector is just uniformly chosen at random something, one vertex in the graph. So that's a special case. What we're going to do here is we're going to take a different choice. And this, I'm not sure, you should know, Kostya, because the original paper for the undirected is yours with Nelly. Where's, you have, the original is undirected, yes. But why the nibble? I remember there's a story in your paper about why the name nibble. Not the original, no, like the paper you wrote with, okay, fine. Yes, this, I remember this. Right, but I'm blanking right now on why the word nibble. What was, okay, we'll leave the story for later. Okay, so PageRank, the original PageRank was introduced by Page and Wren in the late 90s, and it's a very popular centrality measure for the reasons that I've explained. It really does run very, very, very efficiently. When the Q is a probability vector, it has a nice interpretation. It's a random walk, not a standard random walk, because graphs, especially directed graphs in the real world, tend to be highly disconnected, so we don't want to get stuck. So this particular random walk has a little unstucking mechanism, which comes in very handy in many ways. And what we do is imagine a random surfer has a coin at each step, tosses a coin. If it lands heads, it chooses from the outbound edges one uniformly chosen at random. If it lands tails, then it chooses from the distribution probability of the vector Q somewhere else and teleports there. So in that sense, it's a nice random walk, never gets stuck, even if the underlying graph is highly disconnected. Some basic intuition about what the PageRank algorithm tends to do and tends to rank highly. In general, there's two things that PageRank does, and this is more obvious in directed graphs than in undirected graphs. In undirected graphs, things get a little bit fuzzy or get a little bit overlapping or intersected, like the two mechanisms blend. But in directed graphs, what PageRank does is very interesting. It makes highly ranked nodes either those that have a very high integrity or those that have a neighbor who is very highly ranked. And those two don't tend to be necessarily a big intersection between the two. This can be completely separate mechanisms where nodes that are highly ranked because of one reason might not have the other reason. So it's a complementary sort of type of rare event probabilities or events. Yes, right, and that's absolutely true. And when that high degree tends to get very dependent on the high PageRank, on the in-degree, then we go back to basically the undirected case, and these two things blend. The intersection of those two becomes the same, and then you sort of say that's the high degree. That's why I wanted to stay away from the case where it's undirected, because then this difference sort of changes a bit. So in terms of back to the recovery problem, the idea is that this intuition tells us something. So we have a random walk. This personalization, also called the teleportation probability, tells you that you can start your random walk, you start going and visiting vertices until you get the first tail. At that point, you go back to some queue, right? And then I start again from there, and I walk, and then I go back. Now, let's combine that with the intuition that if I am in community 1, then I'm more likely to have neighbors of community 1. So if I do walks, most of the people I'm visiting are from my same community, right? If I keep going back, if I let my walks go too long, at some point, I'm going to go and visit somebody from the other side. So there's a balance between playing with these two things. If I keep my walks close to my community, then chances are I'm going to see everybody in my community. And that's what Nibble does. That's exactly the intuition behind it. So given that we do know a few, we're going to make sure that we run our random walks always starting from the seeds. Why? Because by doing so, we're trying to discover everybody else in that community. The algorithm was pretty simple to explain. We have two parameters that we can pick. That's the damping factor and the threshold parameter that I'm going to call x0. And we'll talk about the threshold in a few minutes. We have a given seed set S, which is a subset of my vertex set. These are the seeds. For now, I'm going to assume that the seeds that I know belong only to the community that I'm looking for. Let's call it community 1. To members of the seeds, I'm going to give them a personalization value of 1, basically. 1 over the number of vertices, but once we rescale it, it's just 1. That means that those are the only ones that I'm going to teleport to. Every time that my random walk is going to teleport, it's going to teleport to a seed. And to everybody else, either community 1 or community 2, if I don't know there are seeds, everybody gets a 0 otherwise. So we never teleport to them. That's the main idea. Then we go ahead and use this personalization vector and compute the PageRank ranks. Then we order the PageRank ranks. And what's going to happen is that they're going to split. The ones at the very top are going to be the seeds. And that should make sense because I keep going back to them again and again and again. But then I'm going to get a thresholding like this. Now, this is a little bit misleading. And I keep telling everybody that maybe we should get rid of this because this is sort of a God picture. Why? Because we put the seeds first between 0 and 200. We put a community 1 between here and there, and community 2 between here and there. So in reality, what you would see is not this nice ordering, but you would still see the sort of the gaps. Exactly. So, as I said, maybe we should change it, just because when you see it, you're like, whoa, what happened? And this is a reasonably, it's a decently sized graph. It has 20,000 vertices. It has 2,000 seeds in community 1. My parameters for the connectivity are 150 and 10. So this is extremely separated, right? It's very, very assortive. And here the damping factor was just chosen to be the standard 0.85. But you can see that it's quite dramatic. And we tried this on many different sizes. Essentially, on an SVM, under great generality, you're going to see something like that. It's quite remarkable.
Your A and B are very far apart.
Here they are, but we did others that are less far apart, and you still see the separation. We ended up going with that one just because I think it has a lot of visual impact. You see these big gaps, and it sort of looks cool, but it goes beyond that. Okay, what is that? That has, okay. I don't know, because it's not how I load it. Oh, darn. Okay, so I'm gonna have to go a little faster. So this is just a nice little picture. A nice picture with a smaller graph so that you can see the effect of what's going on. This is sort of, so what you see is, I think that this was done on Python or one of the Python graphing routines. And the segregation is being done by one of the standard algorithms that the graphing software is using to separate and cluster, but the colors are ours. So they're the ones that are given by our knowledge of which nodes are being classified as community one, and which ones are being classified as community two. Community one is down here. The green vertices are the seeds. All the other sort of orange vertices are the other members that were classified correctly as community one. And then the sort of purple color thing is community two. And you can see there's a few misclassifications of community two as well, but it's actually not too bad. This one is a lot less dramatic in the choice of parameters if you want to take a look. You know, this is the seeds are 15 relative to 300, and the difference is between 10 and 1, but it's, you know, you still see it, and it's small so that you can see it, otherwise it's just a blur. So that's what happens in practice, and although I just showed you a couple of toy examples, we saw that in great generality beyond what I showed today. Now, in terms of what we did, we were looking at the theoretical analysis of trying to say, is this what we're seeing something that is really happening, or something that is on this simulation or on that simulation only? So what we tried to do is we tried to actually get some theoretical analysis of what the misclassification probability is under this PageRank Nibble algorithm. And the idea is, again, we have the algorithm with the two parameters that have to be chosen, X, 0, and C, and we have the sparse SVM, and we want to provide some theoretical justification of why this works and what matters and how you choose the X, 0, and the C, and that kind of thing. Everything I say is for this simple toy example, but generalizes to a lot more complex types of random graphs. We take a sequence of sparse directed stochastic block models. They're going to be on two communities only. They're going to be balanced, so the proportion of vertex community 1 is 1/2, and same for community 2. So that's just for these examples, nothing important. The main assumption, this is going to be true for any graph that we use, even in more general setting, is that we need the type distribution to converge. Control L. So that's the standard assumption that we use for local weak convergence with marks. And that's the existence of some limiting distribution on the type space. The limiting distribution on the type space gives us limiting conditional distributions given the community that are the main thing that allows us to do the classification and proving that there is a legitimate object that one can analyze that has a probability of classifying somebody with one label or another. The main theorem behind this is a local weak convergence theorem at its core. What it says is what we have heard several times since yesterday in Remco's talk and today's plenary talk as well, is that when the graphs have this local tree-like structure, there's often a local weak convergence theorem behind. And then once you have the local weak convergence theorem, that means processes that are being run on top of the graph can be analyzed locally. Any kind of stochastic process of recursion that is local in the graph is going to have the property that you can analyze, that you can exchange the limits between the graph and the local weak limit and analyze the process itself on the local weak limit. And because local weak limits in most of the examples that we know are trees, you gain a lot. You gain a lot of mathematical tractability to do that. In particular, in this case, we have the existence of some random variables that we call Ri. Here, my RIN is a uniformly chosen vertex known to belong to community I. And this is some random variable that is the limiting object that has some tractable properties that we can analyze. These are the joint distributions for the conditional probabilities and the local weak convergence in probability sense. This is the weak convergence standard. More can be said. There's other modes of convergence. I won't go into that. And the nice thing about the limit is because the limit is a tree, then one can analyze these random variables in terms of distributional fixed point equations. And distributional fixed point equations are actually very useful for computing a lot of things. They're quite tractable for the purpose of doing means, variances, and things like that. Just a couple of comments about this. As I said, the local weak limit is a tree. In this case, it's a two-type Galton-Watson process with Poisson offspring. These are marked couplings. Why? Because the out degrees become marks of the vertex. So the marks in this case also have a Poisson distribution. The parameters are given in terms of the kernel and the proportion of each, the size of each community, of course. And of course, the local weak convergence of the graph leads to local weak convergence of PageRank. This is a statement that I'd like to say, it goes way beyond that. Like in modes of convergence, it doesn't have to do anything with PageRank. It's a statement that one can make in way more generality, and that's something that's very interesting and has broader implications. These limiting distribution, once you have it on a tree, can be analyzed via distributional fixed point equations. And I won't go into that. That's another sea of theory, and I don't want to run out too much of time. But it's a very tractable set of mathematical tools that can be useful for many purposes. Just to give you a quick picture of what it is, I personally like to think of local weak convergence in terms of couplings. This coupling works for any directed inhomogeneous random graph. Doesn't matter if it's sparse, it doesn't matter if it's semi-sparse, it doesn't care if it's Chung-Lu or if it's a stochastic log model, if it's whatever kernel you want, whatever number of moments, as long as you have one moment, it's all that matters. So in that sense, it's really nice. And the main idea is you take one vertex at the beginning and you explore in order, in steps, the outbound edges, those become marks, and then do in the next, in the other step, the inbound ones. So we do usually outbound first, the blue ones, the little light blue ones, and then in the next set of steps, all the inbound, so that discovers all these red ones, and then the blue ones in the middle for the outbound of the first generation. Then let's go to the inbounds of the third, and that order alternating, so that we get everything in a breadth first fashion. And again, the only reason why we have this is because these couplings work beyond a lot of things, can be used for many different purposes, and they're quite useful in their generality. The main theorem gives us the characterization of the probability that a randomly chosen vertex in the tree is of community 1 or community 2. And as I said, we wanted some nice computable constants in terms of the parameters of the model. Here they are. These two probabilities are all you need for the misclassification probability, because misclassifying means that a chosen vector has a rank below the threshold or above the threshold, right? So depending on that, this is all you need. The threshold that is implicitly being used here, the x0 is 5 times s/8, where s is the proportion of vertices from community 1 that we know. And we get that the probability of misclassification is always little o of n, of the number of vertices in the graph under this particular choice. Again, none of these is specific to the model, because the probability, the existence of the RIs exists in way more generality. And once you have that, you can do a lot of other things. I'm going to skip this part on the theorem of how one proves that. It's not, I'm running out of time. But I do want to stop a little bit to say a few things about the kind of techniques and what you can obtain from here. You could argue that you can get way better bounds. We did something very rough, like Chebyshev bounds for the paper that was published in this conference, but you could do a lot more, especially if you have a nice, well-behaved stochastic log model with 2 communities and no degree correction. You can also optimize over C and X0, right? When we did the optimization over C, that was really weird. Why? Because we kept oscillating no matter what, the example around the 0.85. Interesting, right? In some way, that is the sweet spot between exploring the neighborhood and getting the main attributes of the vertices that you want. And that seems to work. Like, even if we changed parameters and everything, when we plotted and tried to optimize over C, we always ended up around that 0.84, 0.85. It just kept going a little to the left or to the right. So that was sort of fascinating to see that there is some magic about that number. You can do exact computation. Those probabilities, there are ways of computing it efficiently. We have methods, we have ways of doing that. So technically you could get them and then do numerical optimization over the values. We believe that you could do better than what we computed here if you have seeds in both communities. Of course, the more you know, the better you recover. And more importantly, everything that I said here for the two community case and the specific SVM where every community is homogeneous is not really needed. The main local weak convergence goes through in a lot more generality, and therefore you can do more. We just did it for the classical examples here and to keep everything very pretty the way we did it, but that's about it. One thing that once you start thinking that none of this requires the SVM is what happens when you take more interesting graphs. In particular, as we've said before, I think, Remco, you argued that most graphs are sparse. I would agree. But most sparse are inhomogeneous. Nothing really looks like this. Inside each community, everybody has the same average number of neighbors. That doesn't happen, right? So you definitely want to degree correct those and get a Chung-Lu with community structure and something more interesting. That seems to be obvious when you download Twitter data or things like that. So once you do that, the question that I've always had is, this thing has to fail. At some point, inhomogeneity is going to kill you. And my only question, and I wanted to end the talk with that, with a little open problem, is how quickly? Anyways, if you want to talk about that later, I would love to. If not, let's just go out for dinner. So thank you so much for bearing with me.